The diode is a mainly resistive, nonlinear, passive electronic component with two terminals whose function is to allow the flow of electric current in one direction and virtually block it in the opposite direction. The two diode terminals are called anode and cathode. The electric current conventionally goes from the anode to the cathode following this direction. Opposite polarization of the diode will oppose a virtually infinite resistance. The diode blocks the current, reducing it to zero. Diodes are passive electronic components. In fact, they do not introduce energy into the circuit in which they are inserted and do not require an external power supply apart the input itself. There are many kinds of diodes depending on its use. They can be used in various electronic applications, and they indeed are an integral part of many electronic devices. JAES, in its catalog, offers a wide range of diodes of the major manufacturers. But how is a diode made? We can see that here inside is a semiconductor material. In this specific case, silicon. Theoretically, pure silicon crystal has no free electrons in conduction band. For this reason, the silicon in question has been doped. For doping, we mean that the impurity inclusion is made by diffusing of certain elements. In general, this is obtained by using a very small percentage of atoms spread within a silicon crystal lattice. These impurities, even in negligible amount, change dramatically the crystal electric behavior. These atoms are called donor atoms, since they yield electrons to the crystal lattice of silicon. This creates two distinct parts within the diode with two different charge levels. One part is doped in order to obtain an excess of electrons, and therefore it is negatively charged, while the other is doped in order to obtain an excess of holes and is therefore positively charged. We will call N the negatively charged part and P the positively charged part, thus distinguishing the so-called PN junction. Now we can see that in the N part of the diode, there is a majority of free electrons, while in the P part there is a majority of electron holes, which are the lack of an electron in a position where one could exist in an atom or atomic lattice. In this situation, the part N will have a tendency to release excess electrons, since these will naturally move towards the holes available on the P side. So the border region of the P side is slightly negatively charged, and the border region on the N side is slightly positively charged. A current, called diffusion current, will flow between the two parts and will try to balance this difference in the charges. We can thus see the so-called depletion zone. As there is a positive and negative charge in this area, an electric field will be created which will go from the cathode, K, towards the anode, A. This electric field causes the generation of another current, the drive current, which will try to balance the previous diffusion current. In case of an electric field, an electrical potential will be created and consequentially a barrier potential. The barrier potential is created when the electric field opposes a further migration of electrons from part N to part P. This phenomenon creates some sort of barrier against the flow of electrons. This barrier value is usually around 0.7 volts for silicon. We here now connect the cathode to the positive pole and the anode to the negative pole of a current generator, in this case a battery. By doing this, an inverse polarization or an inverse bias condition is obtained. The electrons and the holes are attracted in such a way to polarize the PN junction to increase the depletion region and consequentially prevent the flow of current. The effect of reverse polarization is to enlarge the depletion region. If we try instead to connect the positive pole of the battery with the P side of the diode, the situation changes completely. The diode will be in a forward biased condition and the depletion region will shrink. Supposing now that our battery has enough voltage to overcome the potential barrier, this will cause the movement of the electrons driven by the electric potential imposed by the battery. When the electrons cross the potential barrier, Their motion no longer meets resistance and will thus more easily occupy the holes in the P zone. Now, the electrons that have moved from the N side to occupy the P side holes, due to the attraction of the positive pole of the battery, will move further, going to occupy the nearby holes and so on, until they flow through the external circuit. This condition is known as direct polarization or forward bias condition of the diode. In a nutshell, the diode behaves like a non-return valve, only in this case the flow is not represented by water but by electricity. Now, let's try to vary the input voltage and observe the diode response. With inverted voltage, we can observe a negligible current. In direct polarization and voltage lower than 0.7 volts, a negligible current is observed. But as soon as this potential barrier is overcome, there will be a strong increase in current. In any case, we note that the voltage across the diode cannot exceed 0.7 volts very much, even in the case of a high input voltage. This depends on the forward bias condition. In this case, the diode places little electrical resistance. In the reverse bias condition, if a very high voltage is applied, the diode could be damaged due to the rapid increase of the current for small increase of reverse voltage applied. The diode characteristic of running the circuit in one direction only can be applied to many electronic devices, such as the rectifier bridge. In the positive half, the circuit will run the current as shown. These two diodes will find themselves in an inverse bias condition, so they will block the current flow. In the negative half, the opposite occurs, so we will get the same current direction on the load. The output can be smoothed further by introducing a capacitive filter and a regulator. Finally, if you found this video useful, let us know by leaving a comment and subscribing to our YouTube channel to stay tuned on the latest release of new videos. Thanks for watching.